So there are basic facts that are involved here, right? So your differential equation differential equation will have a solution that looks like this. Y is equal to e to the mx. Your differential equation will become, I'll put become in quotes, a polynomial. And we know that this polynomial is called the auxiliary equation. And you will find roots for these polynomials. As many roots as the degree of the polynomial, which is the same as the order of the differential equation. Now the roots may have multiplicity. And they may be complex conjugates. Or they can be all different roots. Now, we've dealt with the different roots business. They'll just be whatever the root is, and then e to that root power. If they're complex conjugates, then we have sines and cosines. And then if we have multiplicity, then we take e to the x, and then for each multiplicity, multiply it by another x. Okay? So let's make up 3 problems and try to identify these special cases. Okay? Well, I guess before that, in our summary of facts here, we have multiplicity. We multiply solution by a power of x. Because our task is to generate a fundamental solution, or our task is to generate n fundamental solutions. And if we have multiplicity, then we have the same solution. And to make it linearly independent, we just multiply one of them by x. And for complex conjugates, we actually get y is equal to e to the alpha plus I beta times x, which then reduces to e to the alpha x times e to the I beta x. And this, remember, expands to some sines and cosines. And so you get a solution y is equal to, y1 is equal to e to the alpha x times cosine of beta x. And then y2 is going to be e to the alpha x sine beta x. And since you're getting a pair of them, they're complex conjugates, so they'll have the same alpha and beta, except they'll have different signs. The imaginary part would have different signs. Then you just kind of ignore the I business and then just come up with these 2 fundamental solutions that come from the complex conjugates. Yeah?
So for like y1 and y2, if you were
Yeah, you just ignore the I altogether. Okay? All right, examples. So let's come up with examples. And from an instructor's point of view, if I'm trying to make up an example, I would probably work backwards. I would probably start with the auxiliary equation, and then from there make up the differential equation, and then expect you guys to work through the whole thing. So let's do an example. Let's do an example where we have multiplicity. And so what I'm going to do is I would take out like a computer algebraic system like Mathematica, and I would say, or I can probably imagine doing this by hand. If I want multiplicity, I want to multiply out maybe an x minus 1 times x plus 2 raised to the third power. Where's the multiplied out version? Expanded form, here we go. So basically, I would want to come up with a differential equation whose auxiliary equation looks like this. And then I'll leave it up to you to try to find out how to factor that and solve for this. Okay? So x to the fourth, let me just copy it. And we put it on the side here, and say now my example is going to be the fourth derivative of y plus 5 times the third derivative plus 6 times y double prime minus 4y prime minus 8y is equal to 0. So this would be my differential equation. So what you want to do is you want to find the auxiliary equation, and the auxiliary equation is going to be this. And then now you're going to have to try to factor this, or find the roots, find the solutions. So if you're doing this, you can guess at some solutions. The video that was on before people were walking into the class was a video on factoring polynomials. And so you can watch one of those YouTube videos. But any way you can, try to factor this. So what was the original problem again? It was x minus 1 and x plus 2 to the third power. So my roots are 1 and negative 2, and negative 2 is multiplicity 3. I guess I should have used m for these things, right? We've been using m. Sorry. Let's change all that. So we need four functions that are linearly independent from each other that would satisfy this differential equation. And one of the functions, if I use m is equal to 1, would look like this. So the four fundamental solutions should equal to y1 is equal to e to the 1 times x. Right, that's from this first one. The second one, y2, would be e to the negative 2x. And now, since negative 2 has multiplicity 3, I need another function that would have this solution, except it has to, so these two are exactly the same function, so they're linearly dependent, and so I can't have both of them there. And if I were to use the reduction of order, or we did use the reduction of order one time when we were looking for something that had multiplicity 2, if the second solution that came out of that was the same e to the x, e to the mx function, except multiplied by x. And so it turns out that if you just multiply it by x, you are still going to get a solution. Now, if you do this again one more time, another reduction of order, just raise another power of x, then you should have your complete set of fundamental solutions. Now, if this is still a bit of a question, I think it's worth taking the time to make sure that this is in fact the solution for this differential equation. And we can do that by taking the derivative 4 times and plugging into this function, into this differential equation. So I think let's do that, and instead of me doing that by hand from scratch, I'm just going to punch it out through Mathematica. Yeah?
How do we know that A is
Because when you factor this, and somehow you will factor this, when you factor this polynomial, you got m plus 2 to the third power. So there are several ways to be able to factor these things, to find roots. You can use your calculators, you punch in the polynomial, you graph it, and you ask it to find roots or find out where they intersect 0 or whatever. So I'll expect you to be able to do that. So what we want to do is we want to check to see if our last solution, the y4, is actually a solution for this differential equation. So I'm going to type in y4 is equal to x squared times e raised to the negative 2x power. Where?
Y to the power 4 bracket x.
Oh, that's just that's Mathematica. It means it's going to be a function of this variable x.
Okay.
So x is your input variable for derivatives. So I basically want to check that. I want to check out y for derivatives of x plus 5 times y for 3 derivatives of x plus 6 times y for 2 derivatives of x minus 4 times y for prime minus 8 times y for of x. What's that supposed to equal? That doesn't look like it's equal to 0. But if we simplify it, we do get 0. Okay? So you can double check the work if you want. Or you can just trust your output from Mathematica. But if you were to double check your work, this here is y to the fourth, or the fourth derivative of y, and then this is 5 times the third derivative of y, and then 4 times y double prime, and I guess they might have combined. This is an 8. Oh, I'm lost now. So it looks like they did some simplifying on the way. Well, in any case, if you simplify fully, then you get 0. So that means this is, in fact, a solution. Because your original problem had this thing supposed to equal to 0. So that's a way to check, right? In the very first day of class, we learned how to check if something is a solution to a differential equation by taking that something and taking as many derivatives as a differential equation wanted, and then plugging it in here. Okay, so that's a way to deal with multiplicity. If you have multiplicity bigger than 1, you just keep tacking on the extra x's, x squareds, x to the third, depending on how the multiplicity goes. All right, now let's do another one. And for this next one, I want to do an example where I will have complex conjugates. Right?
So, going back to that example, is there any way where after you plug in, the result is not going to be 0?
If you plug it in and the result's not equal to 0, then this is not a solution. It would be wrong. So, for example, if I tried another y, let's say I thought y sub 5 is equal to x to the third e to the negative 2x is a solution, I would plug that in to see if it works. And so what if I do that real quick?
Are they all supposed to be solutions, or is it
Well, the ones we listed down are supposed to be solutions.
not the same? Are they going to be problems where it's not going to be a solution?
Well, yeah, kind of like in the first test, it's asking you to check something if something's a solution, and then this is how you would check. It's like solving in algebra, and when you solve for x, you just box the answer and you're done, right? So technically, you should plug it back into the original equation to see if it works. So that's kind of like what we're doing. So just to show you that y to the third should not be a solution, the derivative of y to the third looks, or the fourth derivative of y to the third looks like that, but I'm more concerned about plugging into the differential equation. And if I were to plug it in and to simplify, I'm going to get something that's not equal to 0. So I know that y to the third e to the negative 2x is not a solution. Okay. So let's go with another example that I'm trying to come up with. I want complex conjugates. I want a polynomial that's not going to factor. So let's multiply this out. I suppose it's easy enough to multiply by hand, but expanded form. I guess would look like this. So that's my auxiliary equation, and then if I'm writing a test or a quiz, and I'll say, okay, my original problem must look like this. Your dE is going to be the third derivative, so I'm going to write it differently this time. d3y dx third minus d, oops, not partial, d squared y dx squared plus 2 dy dx minus 2y is equal to 0. So that's my differential equation. And if you do the work to get your auxiliary equation, this is how your auxiliary equation should look like. And if you do your work to factor this, you should be able to factor out an x minus 1. Then it should be an x squared minus 2 plus 2 left. Maybe you should FOIL this out and make sure. No. Yeah, so what's going to happen is that you can't factor x squared plus 2, at least not in the real world. And so if you try to solve for x there, because technically x is our independent variable from our differential equation. So if you were to solve for this, we have our roots m is equal to 1 from that first one, but then the second one you can't factor, so m squared plus 2 is equal to 0, and if you bring the 2 over and take the square root, you're going to have the plus and minus square root of negative 2 business, and that negative under the square root means it's an imaginary number. Yeah?
Can you have for the sum function or x or like n minus 1 at like square plus 2
No. No. This only is going to work for complex. No, I'm sorry. This is only going to work for homogeneous differential equations. If we have a non-homogeneous, which is our next topic, we'll talk about it. But when you turn into your auxiliary equation, this is always 0. Your auxiliary equation is always 0. All right. So this is the, I don't know if you want to go through the steps using Euler's formula and all that to come up with a sine and cosine, or if you can just try to remember it. This thing does not have a real part, or if you want to write your real part as 0, that's really all you need to come up with the equation, right? And I called it alpha and beta in the first page of this lecture, so you can just look at it and say, okay, e to the alpha, which is 0, times x, so e to the 0, which is 1, so we kind of just ignore that. And then cosine, the square root of 2 times x, that's the beta. So, how many fundamental solutions are we looking for? We're looking for 3 fundamental solutions. So 1 is going to have an m of 1, so y1 is going to be e to the 1 times x. No. So y2 is going to be e to the 0, I'm not going to bother writing that down, times cosine of beta times x, and the beta is the imaginary part of your root, square root of 2x. And then your third, or your paired up, your second one in the pair is going to be, again, e to the 0 times x times sine square root of 2x. So your fundamental solution, and if you want your general solution, you just string them all up. You just multiply each one by C1, C2, C3, add them up, and then there's your general solution. No, your general solution is a function. So general solution. And I don't put a sub anymore. This is just y. Y is equal to C1 e to the x plus C2 cosine root 2x plus C3 sine square root of 2 times x. And if you take this general solution, plug it back into the original differential equation to check, you should get this thing to equal to 0. Okay? All right, so that's the summary of all these things. Is that a little clearer now? If it's not crystal, at least a little clearer. And when you guys do your homework the night before it's due, you can actually go to the website and find that the lecture notes aren't there, and you panic, and then you email me, and I don't respond, and you say, I can't do the homework because All right. So let's, I forgot to open my, oops, that's my email. I don't want to open my email. That was my email. So our next section is taking a look at non-homogeneous equations. We're still going to be at the linear case, and really we can't really do much nonlinear, higher order nonlinear differential equation. It gets a lot more complicated. So we're going to stay in the first order differential equation. But at least we get to examine case where it's non-homogeneous now. Let's see if I can get there. All right. This is a little summary note that we had from our from 4.1. So this actually pertains to what we're going to do now. So I'll recopy it. And this ties along with what we were just doing. To find a general solution for a homogeneous differential equation, we have to collect the fundamental solutions. And we would expect as many fundamental solutions as the order of the differential equation. And so if we had a third order differential equation, we should expect 3 fundamental solutions. And to find a general solution, you just find a linear combination of those fundamental solutions. Now, for a non-homogeneous differential equation, you need to do one extra thing. It's basically going to be the same work as the homogeneous part, but you have to do one extra thing. Well, let's talk about the same work as the homogeneous part. You're going to get the fundamental solution for the homogeneous differential equation, which is n, however many there are. But you have to add on a solution to that particular non-homogeneous differential equation. What?
A solution?
A solution to the non-homogeneous differential equation. A solution. A particular solution to a non-homogeneous differential equation would be a function that would satisfy that differential equation when it's not equal to 0, when it's equal to whatever it's equal to. So, given that we know how to do this business now with the homogeneous differential equations, we're going to add an extra step for the non-homogeneous differential equation. Okay? So what we need to do is we need to come up with a particular solution to a differential equation. Okay? How are we going to do that? We're going to guess. Turns out that your particular solution, and when they say particular solution here, again, it's one of those words where we use particular solution early on to say that this is a solution to an IVP, initial value problem. Here, it's not talking about, there's no initial conditions anywhere, but they still use the word particular solution. They mean particular as in particular to the specific non-homogeneous differential equation, for what that's worth. Let's see if we can do one of these problems. Okay, so look at these examples of these differential equations. They're not equal to 0 anymore. They're equal to functions. They're equal to non-zero functions. So what we're going to do is we're going to assume that our particular solution that we're looking for is associated with the non-zero right-hand side function of your differential equation. Okay? So let's take a look at the first one. Y double prime plus 3y prime plus 2y is equal to 6. Now I need to guess at a particular solution that would satisfy this differential equation. Let's try 6. It's a good guess. Makes sense, right? It does make sense because your particular solution is somewhat related. I said your particular solution is related to the right-hand side, so it does make sense to guess 6. Now, it's wrong, but but it's a good guess. That's the way to do it. That's the way to start off. And that's how you guys do it in engineering, right? You just guess. Okay. So let's see if we can plug that into this differential equation and get a correct answer. So let's take the derivative and blah, blah, blah. So according to this, we need to take up to 2 derivatives. We need yp prime is equal to 0. Oh, it's 0. Yp double prime is equal to 0. So if I put this in to check my work, or to check to see if 6 is a solution, 0 plus 3 times 0 plus 2 times y, which is 6, is equal to 6. Did that work? It didn't work. How close are we? So what would be another guess? Try 3, right? So let's try 3. So y particular is 3, and yp prime and yp double prime are 0 again. So we get 0 plus 3 times 0 plus 2 times yp, which is 3, is equal to 6. And does that work? So that does work. So that's a particular solution. Okay? So in terms of solving for this particular differential equation, what we would like is we would like now the solutions to the homogeneous differential equation. So now that you've found yp, well, no, because this is a constant, so it turns out to be 0. But if this happened to be like x squared, then you'll have 2x and 2. To actually complete this problem, what we want to do is we want to find solutions to y double prime plus 3y prime plus 2 y is equal to 0. So what we need to do is we need to go back, pretend it's a homogeneous differential equation, and then see if we can find a solution to that. And you guys are all experts in this now, right? After today's very extremely clear summary. Can we factor that? And so we can get the roots. The roots are the -2 and -1. And so your solutions, your fundamental solution, you should have 2 of them because there's a second order differential equation. Let's say call it y1 is equal to e to the -2x, and y2 is equal to e to the -1x. So now you have your fundamental solution to your homogeneous differential equation. Remember, our original problem was non-homogeneous. So to get the final solution, the general solution for here, is going to be y is equal to c1 times y1, e to the -2x. And it doesn't matter whether you put -2x or -x first, it doesn't matter. C2 e to the -x. Now, if this was a homogeneous differential equation, you'd be done. But we have to add the 3 plus 3. Now, that's your solution. Where did 3 come from? The 3 is that y particular that we found. Okay?
So by looking at the function at the very beginning, we're supposed to know that it's not homogeneous, right?
This function? That it's not what?
Homogeneous.
It's not, because there's not 0 here.
Okay.
It's,
This one.
yes. It's not 0, it means it's not homogeneous. And so you have to find a particular solution. Your particular solution will relate to whatever that function is on the right-hand side. Okay, so that was a good first example. We were able to do it by just guessing. And we just guessed, right? But obviously, guessing is going to get you so far. And you're going to have to try to see if you can find a mathematical way of doing this, a more systematic way of doing it. Let's take a look at number 3. Why don't we take a guess? 0? No, 0's not going to work. What? No, probably not 30. So your particular solution is going to have the more or less the same form as your right-hand side of your differential equation. 2x plus 3? Any mx plus b would work, right? Mx plus b. Huh. Let's plug it in. What do we need? We need the first derivative and the second derivative. So yp prime is equal to 2. Yp double prime is equal to 0. Those are nice. And they just become 0. We check our work. It says 0 minus 10 y prime is just 2, plus 25y, which is 2x plus 3. And this is supposed to equal to 30x plus 3. We're going to get, what is this? This is 50x plus 65. One less. 55, right? 55? So this didn't work, but it looks awfully close. Let's start thinking like mathematicians now. So we want to find a system to be able to find this, and what are the important aspects of our guesses that's coming up for us? What needs to be changed in this equation that Juan guessed at? It'll be what? The constant, 3 over 25? Because it still has something multiplying. So these two numbers seem to be the thing that we're changing, right? So why don't we just call it ax plus b. So those are changing. We can continually change that, or we can just drop variables in there and solve for them as we set these two things equal to each other. So let's give that a shot. Yp prime is just going to be a, and yp double prime is going to be 0. So let's plug that into the equation. We're going to get 0 minus 10y prime, which is a, plus 25 times y, which is ax plus b, should equal to 30x plus 3. And if we do kind of some, I don't know, stuff, you get flashbacks of Calc 2, right?
You come up with A has to be 6/5.
Whoa. Slow down. So, Deborah's a little bit ahead of us right now. But what does this remind you of? Partial fractions, right? And these are like the equations that we come up with partial fractions. So it's kind of similar idea. You're looking for the coefficients of those functions. Coefficients of x would be 25a and 30. So we know that 25a has to equal to 30. And then, Deborah, what was it? 6/5. That's your first. In guessing that, we would have never gotten that guess. You got this some weird looking fraction. And then you got 25b minus 10a is equal to 30, or 3, sorry. And knowing that a is equal to 6/5, you can work this out also. So b is equal to what? 12 over 25. Can we get a second on that? All right. So now we have a and b, and now we have the particular solution. So yp should equal to a, which is 6/5 times x,
Yeah, 13,
15 25ths, which reduces to 3/5. All right, so plus 3/5. That should be. Okay, so now we found a particular solution. This method is called methods of undetermined coefficients because we put coefficients here and then we determine them. That sounds like a good name.
when you just substitute 30x plus 3 for 0, your normal homogeneous.
Yep. And then so now we're not done, right, with this problem. We're finding the general solution for this differential equation. All we found right now is a particular solution. And so if we come back to this problem, and look at the homogeneous counterpart when it's equal to 0, we would find the solutions for this, right? And we can do this because we're all experts. M squared minus 10m plus 25. That looks interesting. So it looks like we have 5 multiplicity 2. Right? If you were to factor that. And so now we got y1 as our first fundamental solution is e to the 5x, and y2, because it's the same function, you have to tack on another x in it, and then now we have linearly independent fundamental solutions. And so these 3 things in boxes can just be strung up together as your general solution. There's a c in front of the y1 and y2, but there's no c in front of the particular because that is the particular solution. So we got c1 e to the 5x plus c2 x e to the 5x plus 6/5 x plus 3/5. And then that is your general solution. That cool? Yeah. Yeah, 4.4. So undetermined coefficients is what it's called technically. And then the idea is in this undetermined coefficient is to find our particular solution, and then we go back to our homogeneous solution. Yeah?
Why did you say 25a?
Because I'm looking to match up the coefficients of the x's and then the other term, the constant terms. So just like in the partial fractions, you have these things and you just look at the coefficients of the polynomials and set them equal to each other. So this goes beyond polynomials, right? We could be dealing with exponential functions and sines and cosines. And the idea is that you just have something in front of the idea is to try to figure out what form your particular solution is going to be. So let's take a couple of these problems, and without actually solving for them, let's imagine what form they will take. So for the moment, ignore the differential equation part. Just look at the right-hand side of the equation, which is what we need to focus on. So for the first one, what should your yp equal to? Ax? I'd say close. Ax plus b. So the thing about polynomials is that if you're missing some terms, you have to make sure you assume that there is going to be some other terms that's less than that degree. So this is to the first power, and so we have to assume that there might be something else that would exist of lower power. Okay, so Ax plus b. Similarly, if you have x squared minus 2x, what do you think your particular solution is going to be here? Okay, so there's a plus c business. Okay, now, for this one, there's two things that are being added. Subtracted, added, whatever. And so our particular solution is going to be a string of equations or a string of functions that would represent each of these things. And these look like they're fundamentally different, right? So your yp, if I focus on the x, the 100x squared, what should the particular solution be based on that function? Now, what we need to deal with is we have this other function that looks fundamentally different from the first one. What would you guess your solution would be, your general fundamental solution would look like for this?
Everything back to
Kind of. Okay, there's an x here. I don't know how they write it in the book, but I would write it like this. Ax plus b, or no, I can't use a, b, and c anymore, so I'm up to d. Dx plus, well, it comes after d, e. Dx plus e times e to the x. So I think they write it like this, or sometimes if you distribute this, dx e to the x plus e to the x. Whoa, e and e. Well, capital E is a constant, and our little e's are our exponential friend. Oh, the exponent part, that's a good question. If you focus on the exponent part here, e to the x, your e to the x will remain e to the x, and you don't need to multiply that by anything else. E to the 3x, yes. It'll just be negative whatever it is. It's exactly what it is. So why don't we change this to e to the negative 3x, and let's find our particular solution form for this next one. What should this one be? So the negative 48x squared would give you this, and this is being multiplied by e to the negative 3x, now that I put that negative sign in there. So this is going to be our general particular solution with the undetermined coefficients that you would solve for. Okay? Now, the cosine's a little funny because whenever we see a cosine that exists, we know that there's lurking right around the corner is a sine. Right? It seems like cosine and sine are just kind of together, right? So, can anybody take a guess at what your particular solution might be if you had a cosine 2x? A cosine 2x plus B sine 2x. So this is where you say, oh, I don't see any sine 2x's there. But that's when I tried to preface this whole thing with there's always a sine lurking around the corner. So, right, when you take derivatives of sines and cosines, one is always going to be the other. What? Yeah, the derivative of one is the other with minus signs hanging around different places. And if you were to guess, we guessed the very first problem we did was just a constant, right? We guessed what it is, and we went through the work to guess what it is. But if you just replace it with just one constant and go through the work, you'll be solving for this A like we would have in the first place. Okay? So this is a method of undetermined coefficients. It has limitations, and the limitations are you can't find particular solutions if your right-hand side involves any other function aside from the exponential function, the sine or cosine function, or a polynomial. So if you're talking about a tangent on the other side, or an ln on the other side, or even a rational function, 1 over x, if you're talking about 1 over x on the other side, you can't do this. So you have to do another method. Okay? Norman?
For the last one, how would you get it?
This one or the last one we did?
How do you get it just using it? Because when you take the derivative to 0, and on the left side you only have prime.
Oh, hey, that's a good point.
So that has to be AX.
Yeah, it looks like it might have to be AX. No. Good catch. I didn't catch that, but if you look at this differential equation, there's no constant, there's no y term here. So if you were to have gone with this, you would have had yp prime is equal to 0, yp double prime is equal to 0. So if you were to plug that into the equation to check, 0 minus 0 is equal to negative 3, and a didn't even pop up. So that is a good point. This won't work. And so our second attempt at yp is multiplied by x. Seems to be the general thing to do, right? If something doesn't work, just add an x to it. So let's see. Yp prime is equal to a. Yp double prime is equal to 0. So we have a 0 minus a is equal to negative 3. So a is equal to 3. So that seems to be your particular solution. And if you continue working this out using, you know, some other stuff, you should get the two fundamental solutions and an answer. So, yeah, so we have the issue that this is only going to work for certain things, but at least it's a good start for us to start exploring non-homogeneous differential equations. Okay, for those ones that involve tangents and ln's and all that stuff, we'll reintroduce the Wronskian and try to find our solutions that way. All right, I think that's all I need to say. Oh, well, let's talk about your exams, the makeups. So at last class, I gave you two possible options to make up your exam. One of them is to redo the same exam, except I'm actually going to include the correct version of that one that you couldn't solve. I'll actually have that there, so you have to actually solve it now. And then I'll take the average between your new score, submitted test score, versus the original score. The other option is to take it at the Learning Center, where I will change numbers and problems and stuff like that. So they will, it would look a little bit different, but the general layout is the same. And then you can get the actual score of that, whatever that score is. And you'll get one sheet of notes, and that's it, right? And so that would be available on Monday and Tuesday before class at the Learning Center. So you only have one of those 2 days to make it up. Yeah, Nora?
You know how you only allow us to retake one test?
Yeah.
So if we choose to do it for this one, we can't do it for that.
You can still do it for the other one.
And you just pick which one to grade after.
No, you can still do it for the other
Oh,
one.
you can retake?
Yeah, because this first one, I felt like there were some issues with that problem that didn't work. And so I'm going to give everybody a chance to do this one. And if you want to make up the second one, that my usual makeup is you get the average between the original score and the one that you're going to make up. But this one, I'm giving you an opportunity to actually wipe it clean, retake it at the STEM Center or at the Learning Center, and then do it again. So I would need to know who or how many will be interested in retaking it at the STEM Center, because I have to actually make copies of those tests. If you're going to do the makeup at home and get the average, then that's not a problem, because you're going to print out your own paper and stuff. But if you're going to take it at the Learning Center to erase your whole grade and then come up with a new grade, I need to know, because I need to make that many copies of the test.
Are you asking for each?
So, yes. So, question, how many people are interested in, oh, by the way, I'm also going to grade a little bit. My grading was a little bit lenient on the first test, on the actual test. So this test, I'm going to grading both the take-home and the retake at the Learning Center. I'll be a little bit more picky about the test. So, how many people are interested in taking the test at the Learning Center? I need a head count. 1. Keep your hands up. 1, 2, 3, 4, 5, 6, 7,
Is it okay if I change my mind later?
8. Maybe. I counted you already, right? 8. So there are 8 people. I will make 9 copies at the Learning Center for people to take. Okay? Yeah. The normal test corrections would also be due before class on Tuesday. I will try to post it this afternoon, this evening. You can download the actual test, and then you can start working on it. Yeah?
If you get a lower score in this test, you would take the highest one, or?
I'll take the highest score. I'll be pissed because I had to grade it, but I'll just take the highest score. Yeah? All the problems, even of the ones you got correct, because I might have given you full credit for it, and you might have actually done something wrong. So remember, I'm going to be a little bit more careful in grading. I was a little bit loose and lenient when I was grading the first one, so you have to do everything over again.
Can't ask you for like information on work now that you do this.
If it's a take-home, you can, yeah.
Wait, so the take home, sorry, I'll ask you later.
Okay. All right, so that's the deal. And if you don't see this test this evening, send me an email because I might have forgotten.